What if the next big leap in American military power is not a faster jet or a deadlier missile, but a tiny glass cell filled with atoms? And what if that little cell could quietly tell soldiers where danger is coming from before anyone fires a shot? If you want more stories where strange science becomes real power, tap like, subscribe, and share this with one smart friend who loves future tech. For years, when people talked about military advantage, they usually pictured the obvious things: bigger weapons, more ships, faster aircraft, stronger armor. But modern war does not only run on metal, it runs on information, it runs on timing, and above all, it runs on invisible signals moving through the air every second. Every radio order, every drone command, every radar sweep, every GPS update, every encrypted message between units, every attempt to jam an enemy system, all of it lives inside the electromagnetic spectrum. On a modern battlefield, the side that understands that spectrum faster usually sees first, reacts first, and survives first. That is why a recent breakthrough from the US Army matters so much. In June 2026, researchers at the U.S. Army Combat Capabilities Development Command Army Research Laboratory, also known as DEVCOM-ARL, announced something no one had shown before with this kind of quantum sensor. They demonstrated a sensor based on Rydberg atoms that could measure not only the strength of a radio frequency electromagnetic field, but also its full three-dimensional orientation and the direction it was traveling. In simple terms, the sensor was not just hearing a signal, it was starting to understand where that signal was coming from in space. That sounds technical, but its meaning is very human. Imagine being on a battlefield crowded with drones, radios, decoys, jammers, and remote sensors. Imagine signals bouncing everywhere. Normally, figuring out which signal matters and where it is coming from takes bulky hardware, multiple antennas, or active systems that can reveal your own position. Now imagine a device just a few centimeters across that can quietly detect a wide range of signals and point you toward them with surprising accuracy. That is why this story is bigger than a lab result. Because if this technology keeps improving, it could change how soldiers sense danger, how commanders map threats, how electronic warfare is fought, and how the United States thinks about the next era of defense. And the strangest part is this: the heart of the system is not some giant machine. It is a tiny chamber of rubidium vapor, with lasers pushing atoms into one of the weirdest states in quantum physics. To understand why that matters, we need to slow down and talk about a problem militaries have been trying to solve for decades. Finding radio signals is not new. Militaries have done that for a very long time. The hard part is doing it fast, accurately across many frequencies, and without exposing yourself while you do it. Traditional antennas are powerful, but they come with limits. In general, an antenna works best when its size fits the wavelength it wants to detect. That means different parts of the spectrum often require different hardware. If you want broad coverage, you usually need more equipment. More equipment means more weight, more complexity, more power needs, and more chances to be seen. That creates a painful trade-off. You want better awareness, but better awareness often means larger and more specialized gear. On a battlefield, that is not a small problem. Size makes you slower, complexity makes you more fragile, and active sensing can make you visible. Now put that next to the Army's new result. According to Army and university summaries of the work, the sensor's core is only a few centimeters across. Yet the sensing principle is not tied to the same size rule as a conventional antenna. That is because the real sensing element is the atom itself. More specifically, it is an atom in a very excited quantum state called a Rydberg state. Here's the easiest way to picture it. A normal atom keeps its electrons relatively close to the nucleus, but if scientists hit the atom with carefully tuned lasers, one of those electrons can be lifted into a much higher energy level. It moves much farther out than usual while still remaining bound to the atom. In that state, the atom becomes extremely sensitive to electric fields. Even a faint passing radio wave can disturb it enough to create a measurable effect. So instead of building a big metal structure to catch a signal, you are using the quantum behavior of excited atoms as your sensing platform. That is not science fiction. That is the real principle behind the Army's device. The specific atoms used here are rubidium atoms inside a small glass cell. Lasers prepare them into those highly excited Rydberg states. Once the atoms are in that condition, incoming electromagnetic fields can shift their energy levels. Those shifts can be read out through the laser system. That is how the sensor feels the radio environment. But the new breakthrough is not just that it feels it. It is that it can help describe it in 3 dimensions. Typical sensors often tell you one thing at a time, maybe signal strength, maybe some directional information along one axis. But the Army researchers reported something more complete. They showed that their quantum sensor could determine the field orientation, the polarization behavior, and the propagation direction, what physicists call the K-vector of the incoming signal. The reported directional resolution was about 2 degrees. 2 degrees may sound like a tiny detail. In a lab, it is a number. In the field, it can become advantage. Because once you know not only that a signal exists, but also where it is coming from, a different kind of picture appears. A radio source is no longer just noise in the background. It becomes a location. A drone controller is no longer just transmitting. It is exposing a direction. A jammer is no longer just causing interference. It is giving away a clue about where it is operating. A battlefield that once looked like chaos starts to become a map. This is why spectrum awareness has become such a big phrase in military circles. The modern battlefield is crowded with emitters, friendly systems, enemy systems, civilian systems, small drones, large drones, ground units, vehicles, relay nodes, electronic attack systems. Some are broadcasting openly. Some are trying to stay hidden. Some are deceiving. Some are hunting. The challenge is no longer just to hear signals. It is to separate them, understand them, and react before the other side does. That is where a compact broadband quantum sensor becomes very interesting. Army officials said the system could operate across an extremely broad frequency range, from direct current up to terahertz frequencies, because of the broadband capability of Rydberg atoms. If that promise holds as the technology matures, it matters for one simple reason. War does not happen in one clean band. Real conflict is messy. Signals jump across frequencies. Threats do not announce themselves politely. A platform that can cover a very wide range without needing an entire forest of antennas starts to look less like a niche lab toy and more like the beginning of a serious military tool. And size matters here a lot. The smaller the sensor package, the more options the military has. It could be integrated into mobile platforms. It could support electronic warfare teams. It could ride on drones. It could become part of distributed sensing networks. It could help small units gain awareness that once required much larger systems. In warfare, shrinking a capability without killing its usefulness is often how strategy changes. Think about what happened when cameras got smaller, computers got smaller, satellites got smaller, and drones got smaller. At first, the size reduction looks like an engineering detail. Then it changes who can use the tool, where they can use it, and how often they can use it. Then the doctrine changes. That is the bigger meaning of a sensor like this. It is not only about sensitivity, it is about access. If this becomes rugged and affordable enough, the ability to understand a complicated radio environment may no longer belong only to large, expensive platforms far from the front. It could move closer to the edge of the fight. And that creates the central tension in this story. Because the future battlefield is becoming more crowded, not less. Drones are multiplying, jamming is getting cheaper, communications are getting more contested, GPS interference is spreading, autonomous systems are increasing the number of machines that depend on links, timing, and control. In that world, whoever sees the invisible layer of the battlefield more clearly has a real edge. If this breakdown is helping you see why a tiny quantum sensor could matter more than its size suggests, hit subscribe, leave a like, and share this video with someone who still thinks the future of war is only about bigger weapons. Now let's make this even more concrete. Take the drone problem. Small drones have changed war because they are cheap, flexible, and hard to ignore. Some watch, some strike, some relay information, some jam, some fly in groups. Some are guided directly by human operators, while others follow more automated routines. But almost all of them create some kind of electromagnetic footprint, whether through control links, navigation support, telemetry, or related systems. Defending against that is much harder than many people expected. Radar can help, but radar emits energy and can reveal its own presence. Optical systems can help, but weather, darkness, terrain, and clutter make vision unreliable. Traditional radio frequency detection can help, but it is often limited by band coverage, prior assumptions, and hardware constraints. There is no single magical answer. That is why a passive sensor with broad frequency, reach, and directional awareness gets attention. In theory, a system like this could help identify where drone-related signals are coming from without shouting its own location back into the environment. It could support queuing for other systems. It could help separate signal sources in crowded spaces. It could improve the speed of local decisions. Notice what I said there, in theory, because this is where we need to be careful and honest. The Army breakthrough is real. But a peer-reviewed physics result is not the same thing as a mass-produced battlefield device. That gap matters. And it is where many exciting technologies either prove themselves or fail. The current system still depends on lasers, careful control, and a sensitive setup. David Meyer, the Army research physicist leading the work, has been clear that there is still a long path between the laboratory and the field. The lasers used to probe these atomic states need high stability. Sensitive atoms do not naturally enjoy heat, shock, humidity, vibration, and rough handling. Anyone who has ever imagined soldiers casually pulling a quantum detector from a pocket tomorrow morning needs to slow down. This technology is promising. It is not magic. And that honesty actually makes the story more impressive, not less, because the most important barrier may already have been crossed. The physics question was whether a quantum sensor based on Rydberg atoms could really capture the full three-dimensional direction of a radio frequency electromagnetic field in a working experiment. The answer is now yes. Once a science problem becomes an engineering problem, the conversation changes. Engineering can still take years. It can still cost huge amounts of money. It can still fail. But the world looks different after the basic physical possibility is demonstrated. The question is no longer, can this happen at all? The question becomes, how fast can we shrink it, stabilize it, harden it, and connect it to real military systems? That is a huge shift, and the Army is not trying to solve it alone. Reporting from IEE Spectrum noted that ARL is working with Inflection to help develop a field-ready prototype. That partnership matters because moving from a controlled optical table to a practical deployable device is not just about one clever physics paper. It is about packaging, calibration, stability, electronics, software, cost, and manufacturing discipline. This is often the hidden stage where future power is really built. The public usually notices a technology at the dramatic moment, the first deployment, the first crisis, the first headline, the first time rivals openly react. But the decisive period often happens earlier, while the work still looks boring from the outside. Quiet lab gains, better components, more reliable lasers, smaller packages, cleaner integration, less noise, better error control, field tests, more field tests. Then one day, a capability that seemed distant becomes normal. That is how strategic surprise often feels in hindsight. And if that happens here, it will not be because quantum sensing sounded exciting. It will be because years of invisible engineering made it useful. Now widen the lens. This sensor is not just a clever military gadget. It is part of a much bigger race. Quantum technology has become one of the major long-term competitions between great powers. Not only quantum computing, which gets most of the headlines, but also quantum sensing, quantum timing, and quantum communications. China has treated quantum technology as a strategic priority for years. Europe has its own programs. Russia is still investing. The US military is not funding this work because it is fashionable. It is funding it because leaders know the countries that turn quantum effects into operational tools may gain advantages that older systems struggle to match. And here is where many people get confused. When they hear quantum, they jump straight to the idea of giant code-breaking computers that instantly shatter encryption. That is one part of the long story, and yes, it matters. But quantum sensing may arrive in practical defense roles sooner than fully mature quantum computing. Why? Because the technical challenge is different. A useful quantum computer at large scale needs extraordinary control over many fragile quantum bits, plus error correction and stability that remain brutally difficult. A sensing system like the Army still uses quantum behavior, but it does not need to solve the entire quantum computing mountain. It needs to prepare atoms in useful states long enough to extract measurements. That is still hard, but it is a shorter road than building the machines people imagine when they hear the phrase quantum supremacy. So if you want to understand how quantum may first reshape military reality, do not look only at code breaking. Look at sensing. Look at navigation. Look at timing. Look at what happens when armies can measure the world with far greater precision while giving away less of themselves in the process. That possibility becomes even more important when you think about GPS denial. Modern militaries depend heavily on satellite-based positioning and timing. But GPS can be jammed. It can be spoofed. It can be disrupted. In recent conflicts, those kinds of attacks have become standard tools, not rare exceptions. That is why the same broader ecosystem of Army quantum research includes work on position, navigation, and timing. If quantum technologies eventually help troops navigate accurately without depending on fragile external signals, that could become another major shift. Now pair that with better spectrum awareness. One system helps you know where you are when signals are under attack. Another helps you understand where other signals are coming from. Suddenly, the battlefield becomes less blinding for the side with the better tools. That is what makes this more than a science story. It is really a story about who gets to stay oriented in confusion. And war is confusion. Not the clean kind, not the movie version. Real confusion is layers of partial information, broken links, delayed choices, false confidence, and too many threats arriving at once. Technologies that cut through even part of that confusion can matter more than louder or flashier systems. If you are getting value from the way we turn complex research into clear strategy, take 2 seconds to subscribe, send this video to a friend, and drop a comment with the one future technology you think will matter most before 2035. There is another reason this Army result deserves attention. It shows what patient research looks like. According to the Army, its research community has been investing in quantum science since the early 1990s. And in 2023, ARL was designated as one of 4 Army Quantum Information Science Research Centers. In other words, this did not appear because someone suddenly got excited last week. It came from decades of work, much of it done far from public attention. That matters because breakthroughs often look sudden only to the public. Inside the system, they are usually the result of long preparation. People outside the process see one press release and call it a leap. The people inside know it was built one hard step at a time. The June 2026 result also did not appear from nowhere scientifically. Army researchers had already published earlier work showing that their Rydberg sensor could measure radio frequency polarization and even decode information encoded in that polarization. That earlier progress helped set up the later achievement. In other words, the sensor was already getting smarter before it got this new three-dimensional capability. That is important because it suggests a pattern. The technology is not standing still. It is gaining layers of usefulness. First, detect the field, then read more about its properties, then determine direction in 3D, then improve precision, then make it smaller, then make it tougher, then connect it to other systems. That is how a lab device begins turning into doctrine. And doctrine is the real prize. Because a military edge is not just owning a gadget. It is changing how forces operate because the gadget exists. Once commanders trust a new sensing tool, they plan differently. Units move differently. Drones are tasked differently. Electronic warfare teams hunt differently. Communications discipline changes, ambushes change, risk calculations change. If a compact quantum sensor eventually gives soldiers a richer live picture of the signal environment, it will not simply upgrade one box in the equipment list, it will alter behavior. That is why rival powers will watch this closely. Not because the current device is a miracle weapon, it is not, but because it points to a possible future where quantum-enhanced sensing becomes part of ordinary operations. And once that begins, other countries will have to respond, copy, compete, or find ways around it. This is exactly how technology races intensify. One side proves a concept. Another side accelerates funding. A third side focuses on counters. A fourth side looks for asymmetric ways to avoid the new advantage. Suddenly, the race is no longer about a paper. It is about timelines, supply chains, talent, and industrial capacity. And talent is a huge part of this story. Quantum technologies sit at the intersection of physics, engineering, software, materials, optics, manufacturing, and defense planning. That means the competition is not only about money. It is about who can train enough people who understand both the deep science and the ugly practical realities of getting systems to work outside the lab. That kind of talent base cannot be improvised overnight. So when you hear about a small Army sensor, remember that you are also hearing about decades of institutional memory, university partnerships, laboratory culture, and national strategy. The glass cell is tiny, the system behind it is not. Now let's deal with the biggest misconception directly. Will this device instantly transform war tomorrow? No. And if anyone tells you it will, they are overselling it. The road ahead is full of obstacles. Miniaturization is hard. Laser stability is hard. Environmental hardening is hard. Calibration is hard. Packaging delicate systems for real military abuse is hard. Integrating a new sensor into existing command and control systems is hard. Testing it against real adversary signal clutter is hard. Keeping it affordable enough to matter at scale is hard. But none of that should make you shrug. Because there is a difference between saying a technology is not ready tomorrow and saying it does not matter. Some of the most important military technologies in history spent years in that uncomfortable in-between stage where they were too early to deploy widely, but too important to ignore. That may be exactly where quantum sensing is now. And timing matters here for another reason. The defense world is already under pressure from the possibility of future quantum computing attacks on current encryption. Security planners worry about what is often called harvest now, decrypt later, where adversaries collect encrypted data today in the hope that more powerful quantum computers may crack it in the future. That is one reason post-quantum cryptography standards became such a serious priority. The United States does not need to wait for a code-breaking quantum machine to appear before adapting. So on one side, quantum creates new risks. On the other side, quantum creates new sensing advantages. Defense planners have to think about both at once. That makes the whole field more urgent. And it also explains why honest observers keep separating hype from reality. Quantum computing may still be years away from direct large-scale military use. Some Pentagon discussions have suggested longer timelines for truly operational impact. But quantum sensing is moving on a different clock. It is closer to physical application because it asks a different question. Not, can we build the ultimate quantum computer? But can we use quantum behavior today to measure the world better than classical tools can? That is a more immediate contest. And it may prove more influential in the near term than many people expect. Imagine a future patrol carrying compact passive spectrum sensors that quietly highlight suspicious transmissions around them. Imagine a vehicle system that helps sort drone control signals from background clutter. Imagine distributed sensor nodes that help commanders build a live map of emitters without relying entirely on conventional antenna farms. Imagine pairing those tools with other quantum advances in timing and navigation. None of that guarantees victory, but it changes the starting conditions of the fight. And that is often enough to reshape outcomes, because modern conflict is not won only by who hits hardest. It is often shaped by who understands the situation faster, who stays coordinated longer, who locates hidden threats sooner, and who can keep making good decisions while the other side drowns in confusion. That is the deeper emotional core of this story. A battlefield is terrifying, partly because people do not know enough, fast enough. Better sensing is not just a technical luxury, it is a survival advantage. It can mean earlier warning, better positioning, smarter choices, fewer blind moves, more time. Sometimes war turns on very small amounts of extra time. And that is why a few centimeters of glass and vapor can matter. Not because it looks dramatic, because it might quietly buy clarity where clarity is rare. Before we close, if you like videos that cut through hype and tell you what really matters, share this one, subscribe for the next deep dive, and hit like so more people can find serious stories behind the headlines. So what should we take away from all this? First, the Army's June 2026 breakthrough was not just another flashy use of the word quantum. It demonstrated a specific capability, a Rydberg atom sensor measuring the full three-dimensional direction of radio frequency electromagnetic fields with directional resolution of roughly 2 degrees. Second, the reason it matters is not mystery. Modern warfare depends on control of the electromagnetic environment. A smaller passive broadband sensor that can help reveal where signals come from could become extremely valuable. Third, this is not a finished battlefield product. The physics milestone is real, but the engineering road is still long. Lasers, ruggedization, integration, and scale all remain serious challenges. Fourth, that does not reduce the importance of the achievement. It clarifies it. The barrier that has been crossed is the barrier of possibility. The rest is the race to implementation. And fifth, the biggest story may not be this single sensor by itself, but what it represents. It is one visible sign that quantum science is slowly moving out of theory and into the architecture of national power. That shift will not always arrive with fireworks. Sometimes it arrives as a paper, sometimes as a prototype, sometimes as a partnership nobody outside the field notices, and sometimes it arrives as a tiny glass cell filled with rubidium atoms, sitting quietly on a lab table, doing something that old hardware was never built to do. That is when history starts to bend. Because once a military can sense more of the invisible world, it does not just gather more data. It changes what can be known in the moment. It changes what can be hidden. It changes who moves with confidence and who moves with doubt. That is the real reason this quantum breakthrough could reshape US defense. Not because it replaces every existing system, not because it turns war into science fiction overnight, but because it points toward a future where the side that masters the quantum layer of sensing may see the battlefield with a clarity the other side cannot match. And in war, the side that sees first does not always win, but the side that fails to see usually loses. That is why this tiny device matters, and that is why the race around it has only just begun.